Here we're looking at the current flow density at 1 gigahertz animated over one period of time in copper hurdles on top of the solid copper surface. And the skin depth is 2 micrometer. And as you can see, currents prefer to flow below those hurdles in the solid copper. So if you take a look at the current flow density at 1 terahertz here, the skin depth is 0.1 micrometer. And you can clearly see currents getting smaller inside the structure. So the currents are flowing on the surface. And the wavelength here is still 300 times larger than this size. Here is how the whole structure looks like. It's parallel plate waveguide with almost TM wave, with 2 magnetic walls here, 1 perfect electric conductor, and solid copper with 1 micrometer grooves at the bottom. So if you take a look at electric field at 1 terahertz, electric field is z-directed almost, with a small component along the x-axis, which makes this not exactly TM, but rather TM 0. And the transverse magnetic field looks like this. So we can see that it gets between those hurdles, or into the grooves at 1 terahertz. If you return to macro scale, take a look at another look at the currents at 1 terahertz and magnetic fields, and then take a look at currents at 100 gigahertz. 100 gigahertz skin depth is about 0.2 micrometers, so it's about half of this size. You can still see that currents are flowing over the obstacles. So what about 10 gigahertz? 10 gigahertz currents start flowing below the obstacles. We can clearly see it, but there is a fair amount of current on the top, so they are still participating in absorption of energy at 10 gigahertz. And what about the magnetic fields at 10 gigahertz? Well, that's how they look like together with the volumeric current density. That's really interesting.